Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss about the hydrodynamically smooth and rough boundaries. So before going to this smooth and rough boundaries, let's try to understand what is this hydrodynamical conditions. This hydrodynamic is nothing but actually this is the method or this is the way which will relate the fluid properties, the mechanical fluid properties to the fluid in motion. When the fluid is in the motion condition, that means when the fluid is in flowing condition, so this will be involved in the involving the mechanical properties in that particular object. So that is, we can say, when the fluid is flowing and involving of these mechanical properties in these fluids. So that is one kind of, we can say, about the hydrodynamics. And it also will be described, this is fluid flow. Let's write one point. And we can say another things. It also describes how the force or how the motions are interacting with the fluids. Okay, how the forces, or you can say, and motions, or you can say motions, how it is, interacting. So it is, yeah, how it is interacting within the fluids. So the fluid means we know that it may be a liquid or it may be a gases. Okay, anything can be possible. So how the fluid behaves in different conditions. So how the fluid is behaving different conditions. So what is the behavior? What is the behavior of the fluid? So all these things will be coming under this hydrodynamical study. So in this study also we have different applications are there. Without an application, nothing will be accepted, you can say, in that. So mostly applications are there in this also. So if you suppose design some kind of ships, or you can say the airplanes what we are designing, let design something airplanes or ships, or you can say the pipelines. What are the things in engineering you can do in that, so that the fluid will be flown through these things. Okay, now if you go for the science application, this is about the engineering application what I'm telling you. And if you go for the science application, like we can say the weather patterns, okay, to understand the weather patterns, how the weather will be, okay, forecasting the weather. So this is weather patterns. And we can say the current in the vessels, okay, the vessel currents. Apart from that also, if you see in the biological study, okay, or in the medical study, you can say, so there we can identify how the fluid is moving through the living organisms. So the fluid movement in living organisms. So these are a few examples I'm giving about the hydrodynamical study. Okay, yeah. Now we'll go for this smooth and rough boundaries, because this all the things are necessary. Okay, and if you see this diagram here, two diagrams I have taken here. One is laminar sublayer, another one is turbulent boundary layer. This is, and this is laminar sublayer, and this laminar sublayer also given here, but this is for smooth layer and this is for smooth boundary, and this is for rough boundary. So I'll come to this point. First, let me give you some brief discuss or conceptual knowledge about the flows. Actually, how we can identify whether the flow is laminar condition or whether turbulent condition, already we have discussed previously. Now, based on the Reynolds number, we know that we can identify whether the fluid flow is laminar, turbulent, or transition. So based on this formula, we know that Reynolds number can be identified. Okay, so in the based on this, we can see, let me draw another one diagram for this. So actually the diagram will be in this way. This one actually we have not discussed in the detail, or in it will become in the boundary layer theory. So just I will give a little hint to understand this concept. So this boundary layer, if you see, this is actually boundary layer. Okay, this is actually boundary layer. So in this boundary layer, when the fluid is flowing over a plate, this is the condition actually given when the fluid is flowing over a plate. So this plate is there, and this is the fixed one, we can say. and two things are will be there. One is free over a free surface. Another one also we can consider inside a pipe. This is inside a pipe condition, and here you can give this center line and how the fluid is flowing through this also we can describe here. Okay, these are the two different conditions I'm showing you. Okay, let's see here. So this is the boundary layer. As I told you, this is the boundary layer here. Now in this boundary layer also, it is having three different zones and three different boundary layers are there. So what are the zones are there? Let's me. So this is, suppose one zone is there, and this is another zone is there, and this is another zone is there. So actually, this is you can say this zone is laminar zone. So I can write. Let me write LZ. This is laminar zone. So how this laminar zone will be calculated as per this formula? Okay, for that also some formula is there, like some conditions are there. The X value will be something, then we can identify that Reynolds number within 5 lakhs. Okay, that is different. When you will study this boundary layer concept, that there will discuss. Okay, and this is laminar zone. And next, this is our transition zone. This is our transition zone. And after that, what we'll get here? This is about here turbulent zone. So this is again same TZ I'll write, but this is turbulent zone. This is transition zone. This is laminar zone. So all this zone, okay. So how we can identify based on this Reynolds number as I told you. So this is the laminar zone boundary layer, or we can say not laminar zone boundary layer. We can say this is laminar boundary layer, because the laminar conditions of flow is here. And similarly, this is transition boundary layer, and this is turbulent boundary layer. Okay, so this is about when the fluid is flowing over a flat surface. So this is, suppose the fluid is flowing with a velocity of u, and here if you see the formation of boundary layer will be like this if there is a plate is there. Okay, now here actually if you see at this turbulent boundary layer, because we are discussing about the turbulent boundary layer. In the laminar boundary layer, that much problem, that much difficulty will not there. All the things issues will come in this turbulent boundary layer. So here there will be a layer formation will be there actually here in this. You see, very small layer formation will be there at this turbulent boundary zone or turbulent zone actually. So this layer is called laminar sublayer. Laminar sublayer. This one. This is laminar sublayer. Now, why this laminar sublayer will be generated here, how it will be created, so that in depth we'll discuss in this boundary layer theory conditions. So now just try to understand this condition. This is actually laminar sublayer. When the fluid will be flows over the surface, we know that there is a viscous effect will be there at this surface level. Okay, at this level, if you see, same condition also here also same thing will be there. When the fluid is flowing, at this boundary zone, at this wall of this boundary, you will get very, the velocity will be negligible, you can say. So at this zone, we won't get that much flow velocity. That's why we used to consider the velocity at this zone is 0. And near to the surface, again, a little bit it will be in the increasing mode. So this here also, at this zone also, we used to call this is a laminar sublayer. That means at this zone, the flow will be laminar flow. Okay, at this zone, the laminar, though the zone is turbulent or the turbulent boundary layer is there, but at this height, at this position, your flow will be laminar flow, because due to the generation of surface, like some kind of roughness will be there at the surface, or some kind of, you say, particles will be settled here, or you can say some kind of roughness was generated or at this position. So various reasons are there for that also. Okay, so at this point, this is your laminar sublayer, and this laminar sublayer is actually indicated by delta star. Okay, now this is also same thing. This is your delta star. Okay, so I hope you understand. It is basic things. Now we'll go for actually this smooth boundary and rough boundary actually. Now two diagrams I have given here. So actually K is there. One term you can see K, another term is delta star. So K is nothing but this is the average height of the irregularities you can see. These are the irregular formation of boundaries, liquid layers are there. Okay, it is very thin layer. This one, if I'm saying, this is very thin layer. At this thin layer, you won't get that much constant here. Okay, that means this thin layer is very small. That will be not visible. Okay, only we can get this when you zoom this by the suppose high-speed camera. If you want to see these things, it is just very difficult. Okay, and in the pipe condition, if you see at this pipe condition, in this pipe condition, if you see, many pipes are, these pipes are made of different materials. We know that some PVC pipes, stainless steels, or different materials are there used to prepare the pipes. So if you touch the surface of this pipe, at the surface, you will see some kind of roughness. So that roughness means that is the these are things, irregularities of the surfaces at this point. So these irregularities, how it is formed? Now when there is a turbulent boundary layer, see, as I told you, this when the laminar sublayer is generated here, now when there is a turbulent boundary layer, at this laminar zone you won't get any kind of turbulent zone or laminar sublayer. Here also you won't get that much, but when you come to this turbulent boundary layer, at this zone only we are able to get laminar sublayer. Above to this, as I told, above to this laminar sublayer, we have a turbulent boundary layer, which is given here. So this is the zone. Okay, now, so okay, let what I've stopped here, K. Here two things are there. One is K, another one is delta star. So K is nothing but K is the average height of the irregularities, okay, which is projecting from the surface. Now you see, this is the surface is there, and here also this is rough and this is smooth. So see, concept is same, but only the thing is difference of this K value and delta dash value, that I'll show you. So K is the average, I can say this is average height. This is our K, and delta dash is nothing but, as I told you, laminar sublayer. Laminar sublayer. Okay, and here actually this smooth layer, a smooth boundary and rough boundary, it depends upon the K values. Okay, so okay, let's discuss about in that. Okay, so now I'll take some conditions here. Okay, now at this laminar sublayer, your eddies formation will be there at this turbulent boundary layer zone, or you can say this turbulent. Here there will be no eddy formations will be there, but at this condition, if you see, eddies will be formation at this point. The eddies is nothing but these are the liquid. It will be like a curve shape. It will be formed at this point. Okay, eddies formation, that is actually, yeah. So that I'll discuss in this point. Actually we'll discuss more details in the boundary layer conditions. So let's see here what is the smooth and rough condition. Actually this all the things we are discussing for the turbulent flow. So when this turbulent flow analysis we are doing, actually this is divided into two portions. Already we have discussed in the previous lecture also. 2% divided, one is what? The first portion is, it consists of a thin layer, as I told you. It consists of a thin layer near to the surface, near to the boundary, you can say. Okay, and in this actually viscous shear stress is dominating. Okay, viscous shear stress is nothing but, we have already discussed, tau V. That means the shear stress which is affected by the viscosity. As I told you, there is a viscous effect is there here. That's why the flow will be very low. You can, the flow velocity will be very less. That's why velocity is negligible, as I told you here. Okay, so here the viscosity effect is there. That's why you can say at this near to the boundary, okay, the viscous shear stress is dominating, while the shear stress in the above of that zone, that means above to this one, okay, apart from this, at this condition, okay, here turbulent effect will be there. Okay, turbulent effect will be there. That means another one, shear stress T, shear stress, that means shear stress with the effect of turbulence. Okay, now at this viscous region, your turbulence will be negligible. You can see here at this region, our turbulence is not there. Only laminar sublayer is there. So there is a effect of laminar flow. Or that means here the flow is laminar. That's why it is called laminar sublayer. Why it is happening? Because of the viscous effect. And at this condition, there will be no turbulence effect. Okay. And this zone and this portion is known as laminar sublayer. Already I told these things. So again, you can remember. So this is laminar sublayer. Okay. Now, at this, up to this height, the effect of viscosity, okay, that is denoted by this delta star, as I told you, laminar sublayer. Okay. And this is first one, this one. And second one is what? Second one is, as I told, the shear stress due to the turbulence, which is compared to the, which is very, very large compared to the viscous turbulence, shear stress due to the viscosity. Okay, and that is known as the turbulent zone. So all these things already I told. This is again I'm telling for your better clarification. Okay, this is all the things. Now we'll go for this K value. This K value, what we are seeing here, as I told, this is the average height. So this average height is nothing but you can see the irregularities of this fluid, which is there due to this, due to the roughness of this boundary. This is a smooth boundary. See, both roughnesses are there, both the boundaries. But as this is the laminar sublayer is there at this point and the K value is less than the delta dash, so it is called as a smooth layer, smooth boundary. But here if you see, the K value is, more than this. The K value is more than this delta star. Okay, delta star is what? Laminar sublayer. So when it is more than this one, that boundary is called rough boundary. Okay. So let's discuss again in this more. First condition is what I told. This K point you can see. Now, the average height of this K, okay, for this irregularity is what you are seeing. Here if you see the irregularities, this is the height of K. Here it is something different will be there. So average height of this, that's why I'm telling average height. So everywhere it is not same. Okay, all these points, the K values are different. So the average value of K for this irregularities, which is projecting from the surface. That means this point, it is projecting from the surface. Okay. Here you can see it is very, very less than the delta star. Okay. So your K value is less than the delta star or delta dash actually. So this is in this condition actually it is called smooth boundary. This one, this is called smooth boundary. First one you can say this is smooth boundary, and second one, and why this smooth boundary also happened, I already informed you. This means what we have discussed till now, that is about the smooth boundary, and this is because of the laminar sublayer of the fluid flow is turbulent. Okay, because turbulent is there here, and at this point due to viscous effect there will be no effect of turbulent in this point, and the eddies which is present, the eddies will be present in the turbulent condition, not in the laminar condition, keep in mind. Okay, so the eddies which is present, that will be in the turbulent flow, and that will be actually, this eddies will be present here at this point, not in this bottom, and which will, this eddies will be try to penetrate the laminar boundary layer. This one, this is the laminar boundary layer. This one actually, laminar boundary layer is this one. So this sublayer also, this eddies work will be there now, to disturb these things. But though this is a laminar sublayer, so eddies will be there at this above to this one, turbulent boundary layer. Okay. But due to this thickness of this, this laminar sublayer thickness, okay, eddies are not able to reach to the surface, to the irregular surface. That's why it's a like covers type. Okay, you can say. So that the boundary behaves a smooth boundary. That's it. And this is called as the hydrodynamically smooth boundary. This hydrodynamically smooth boundary. This is the first one. I hope you understand this. Now, second one, again, similar, same thing. There is no difference of that in that. But the concept is here actually, if you see second one. Yeah, here also again, the Reynolds number is increased because see here Reynolds numbers are less because the laminar flow. Now when turbulent flow will be there, now when the Reynolds number will be more, then we can get the turbulent flow. So there the thickness of this laminar sublayer, you can say, will started decreasing. That means it won't go up next. So here the turbulent zone started and turbulent boundary layer, that laminar sublayer is less here. So that if, now condition came, if the sublayer becomes, which sublayer? The laminar sublayer. This is second condition. If the laminar sublayer delta dash, okay, is much lower than the, or much smaller than the, which one? K. That means K is more than the delta star. Okay. And that is called your rough boundary. That is called the, this is smooth boundary and this is called rough boundary. Okay. Yeah. And why this is happening? Now this is because of this irregularities of the surface which is above the sublayer, because this is the sublayer is there, you can see this is the sublayer, laminar sublayer, and above lot of portions are there, that surface. Okay, that's why the irregularities of this surface which is above the laminar sublayer, here it is inside and this is above. That's why the eddies which is present here, eddies was present above, now here eddies is present inside this, okay, which is present in the turbulent zone, that will be come in contact with the what, in this surface. Okay, and due to that the losses of energy will happen, loss of energy, lots of energy is going to be lost here. Okay, and this boundary layer is called hydrodynamically rough boundary. Hydrodynamically rough boundary. I hope you understand this concept. Yeah, so this is about the hydrodynamically rough boundary. So actually one scientist, again, he did some experiment on that. So from that experiment, what he got, I'll write here. The scientist is nothing but Nikrudse, and Nikrudse scientist, he given some by this, from this experiment he given some value. I'll write here what he given. When the value, or if you can say the value of K by delta star is less than 0.25, then it is called smooth boundary. Then it's called smooth boundary. You can remember this K by delta star. Now see, this is the K value and this is the delta star value. Obviously when this K value is K by delta star is less than 0.25, this one, yeah, when it is less than 0.25, then we can say it is a smooth boundary. Similarly, for the rough boundary also value is there. For the rough boundary, actually when it is greater than 6, different, because if you see the diagram here, yeah, this is K value and this is delta star value. Okay, now see, K divided by delta star is less than 0.25, then we can say it is a smooth boundary. Similarly, for the rough boundary the value will be different. So for the rough boundary, the K divided by delta star is greater than 6, then it is called rough boundary. Okay, now another one condition, if the value of this K by delta 2 in between these two, that means you can say the value 0.25, again it is greater than this, less than this, that is K by delta star, and this is 6, then it is called the boundary is in transition. Actually the boundary is in transition place, smooth, rough and transition. So in terms of, if you the roughness, if you consider in terms of Reynolds number, because as I told you already, Reynolds number rho v d by mu. Similarly, in terms of roughness of Reynolds number, we can write rho v d by mu, or also we can write this is v d, only v d by nu, because nu equal to viscosity by mu by rho. So for this condition, again, if you want to convert in this, so for this also given, if this Re less than 4, okay, the boundary is called smooth. The boundary is called smooth. Similarly, again, Re is greater than, Re is greater than 100, then it is rough. Because in the Re, again, velocity is there. Okay, so that will also indicating that one. Now again, if the Re value is in between, lies between 4, similarly we can write here 4 Re, and this is 100. So this is in the transition stage. This is in the transition stage. We know that laminar, turbulent, and transition. Similarly, smooth is there means laminar, and this is more than rough means turbulent, and this in between this means transition we can consider. So this is all about this concept of hydrodynamically smooth and rough boundaries. I hope you understand. It's very, very simple. Only things need to be remembered this one. This all this summary, we need to remember this K value. K less than delta star. K less than delta star is smooth boundary. K more than delta star is rough boundary. Why this K is less? Why this K is more? That I have already told you. And what is this delta star? Laminar sublayer, and this is the height of the irregularities of this liquid or fluid. And these are some values need to be remembered. So I hope you understand. If you are having any doubt regarding this, you can give a comment on the comment box. Thank you all.